Hello, everyone. So I'm, as Ryan said, I'm Martin from Infinio. I am going to talk about making enterprise software that's as easy to install as Dropbox. And I work at a company called Infinio. So what does Infinio do? We sell software to small and medium businesses that speeds up your storage. So if you have a virtual machine infrastructure, we work with VMware. The ESXi there, think of those as physical machines. They all talk to a central storage in the back end. And we add a new virtual machine to each host. And we use some of the RAM on there, some of the CPU and RAM that you're not using to have a RAM cache. We also dedupe across within machines and across machines. So we're a distributed dedupe cache. OK, so we want to make our software easy to try out. We're a new company. People don't know about us. When I searched for enterprise software, just enterprise software, nothing about hard to try out or anything, just enterprise software. Image search on Google, this was one of the links that came up on the first page. Enterprise software has a reputation for being hard to try out and being somewhat cumbersome. So we wanted to have a minimal user config. When the user goes to try our stuff out, they just have to type in the credentials for their virtual machine infrastructure, which lets us programmatically insert ourselves. They have to say which NFS mounts they want us to accelerate. And then we have a control panel, which is a web-based thing. So they give a username and IP address for that control panel. And that's about it. It's as simple, as little information as possible. We want to be easy to install. So this means no interruptions. If you have to stop the VMs in order to put them into a different kind of storage system and then start them again, this means it can't be done during the day when people are using their VMs. It means you have to do it during a maintenance window at night or on the weekend. And it's a big deal to try to do this, and that's a big barrier to just trying our stuff out. So no interruptions, no drops, no VMs. We also have no hardware. We're a software-only solution, no rebooting anything. And we're also easy to uninstall. So that's, of course, you might think that goes without saying, but sometimes the uninstall path is different than the install path. No data migration. Other competitors, again, you have to convert the format that the virtual disks are in, and that, of course, means they have to be offline for a while. And throughout all of this, we do all this while still intercepting I/O. Right, so how do we do this? All right, so let me tell you the goals for this talk. It's not so much the details of virtual machine infrastructure. I'm assuming most people aren't that interested in that. But kind of the moral here is that intercepting I/O is hard, and we have a choice. We can either put that complexity on the user by telling them, you're going to have to move things and do all this stuff to get it into our appliance, or we can put it into our software. We chose to put it into our software to make things easy for the user. So there's often that trade-off. We're also going to do some deep networking hacks in real life. So I'll show you all the stuff that you should have learned in school if you were paying attention about how TCP works at lower levels and all this sort of stuff. We're going to do a refresher on that or explain it to people who didn't know it and show how you can actually do some fun things with that in real life. We'll learn about the networking protocols. OK, so this is the situation before we install. The host here is a physical machine. Like you go to Dell and you buy something and it has 6 cores and blah, blah, blah. Inside there is a virtual network interface card, which has an IP address. And there's a virtual switch. So switch is just a networking switch. You plug lots of Ethernet cables into it. This is a virtual switch, so you just click on some things. But it does the same job as a physical switch. And then it talks over real physical networking to the storage, which has a different IP address. Right, so if you want to intercept this traffic, right, what are you going to do? Suppose you want to make a cache, right? So you want to instead of sending it to the storage, you want to send it to our software. Our software will forward it to the back end if we don't have it in our cache. Otherwise, it'll apply for it from the cache. It'll also update the cache. Right, what would you do? Well, this is basically the definition of a proxy. So the straightforward thing to do would be have this separate cache virtual machine that has 2 virtual network interface cards with their own IP addresses. And we just tell it to send, instead of sending it to the back end, send it to us. The problem is you can't just change an IP address midstream. So if you have an NFS volume mounted on your computer, and you say, hey, this IP address, instead of sending it to here, we're just going to send it to this other place. But trust me, it's all the same data. Nothing will be different. You won't even notice. But just change this IP address for me. Right? That doesn't work. In order to change an NFS mount, you have to unmount it, which means stopping all the access to it. You have to shut down VMs. And then that's not easy to install. So we can't do this. Right? So what do we do? Well, in order to know what to do, we're going to have to go into the details of networking. So here's the 7-layer model. Don't worry, you don't need to know all of this. I'll explain the parts you need to know. The ones that we're probably most familiar with are layer 3. This is where you have IP addresses. They're worldwide. So if you want to talk to a Facebook server in Japan, you find the IP address of that. It's used throughout the world. Anywhere in the world, you can type in that IP address, and it will connect there. Below that is what's called the data link layer, and this is MAC addresses. If you ever installed a router or something and you had to call up Comcast and read them the 6 pairs of digits on the back, that's a MAC address. And the concept here is the local area network, all the things that are kind of connected together into one switch or a bunch of daisy chain switches are a LAN. All right, so what is a LAN? So who remembers back in the day when LANs were actually made, when Ethernet was kind of new and you had the B and C connectors and the coax cables? Who remembers that? Yeah, some people? OK. So LAN is originally the broadcast domain. When one of those cards is talking, all the others can't do any talking. They'll all hear the traffic that everybody else says. They have to filter it out. So each packet has the MAC address of its destination. And if that doesn't match your MAC address, you just ignore it. And if it does, you do it. So a LAN was originally a broadcast domain. But then there were some interesting things happen. So one is that, so there were kind of 2 things that go together. So one is that they stopped having this broadcast where everybody was using the same coax cable, and now they have actual Ethernet cables. And so you can send data on one. You can be sending data on multiple of them and sending in multiple of them, sending it out to some others, and they can all talk. But the concept of LAN is still the same. It's still all the computers connected to the same switch. And there's still a concept of broadcasting information. So for example, when you go to discover a printer, right, you can discover printers on your LAN. When you do a LAN, when you're playing Minecraft or some other video game, and you do a LAN game, you can discover other ones that are on the LAN, but not ones that are in your neighbor's house on a different LAN. So this concept of LAN had these kind of 2 competing ideas. One is the physical thing connected to the same physical switch. The other one is a subset of ports. So the other one is the things you can discover, right? And basically, there are good reasons to want to separate these, right? If you're the IT administrator and you want, the salespeople have their printer, and then the HR people have their own printer, they might be plugged into the same switch, but you don't want them using each other's printers. So there's this concept of the virtual LAN. You can say, hey, all these ports on the right from 13 up to 20, whatever, those are going to be one virtual LAN. Everything plugged in there will be able to broadcast and see each other, but they won't be able to see the things on the left. And things on the left will be able to see each other, but they won't cross over between the left and the right. So there's this concept of virtual LAN. So the first thing we do is we create inside the switch, and this can all be done programmatically, we create a virtual LAN to put and we switch the network interface card to be on our new virtual LAN. So the green on the left is the new virtual LAN. And now you can imagine that we would pretend to have the IP address of the storage. So now the cache VM on the bottom, we have the same IP address as the storage. And on the top, we have the same IP address as the host. So now we're kind of spoofing each one to each other. So the virtual LAN piece of this works. But the problem with this is, what if you have other machines on the outside in the storage? There may be more than one storage box. There may be lots of other things you're talking to out there. We can't pretend to have all these IP addresses, and it gets complicated really quick. So this is where we get down into how the LAN actually works. So every device on your LAN has a MAC address, and it has an IP address. And again, these IP addresses are kind of static, even though the paths of them may change. So the question is, if this guy wants to talk to this IP address, what does he do? Well, he broadcasts a message called an address resolution protocol, ARP, and says, here's my MAC address. I don't know which destination MAC address to send this to. I'm broadcasting it. I'm going to say, who has this IP address, and tell me my IP address. So this is an ARP message. And then in this case, the router, because it's not one of these IP addresses, because it's in the outside world, which the router controls, the router says, hey, send it to me. So here's my IP address of the router. I'm sending this message back to the guy who asked at his MAC address. And if you want to talk to this IP address, you send it to my MAC address. All right, so this is great. So what we do is we actually do what's called Proxy ARP. When this guy sends out saying, hey, I want to talk to this 18.10 guy, the storage guy, tell me what the MAC address is, we send back a message saying, talk to our MAC. And and similarly on the other side, on the storage, when it wants to, when it's asking who should we talk to, we say, oh, don't talk to that old MAC address that you used to talk to. Talk to the other MAC address for the other network card in here. OK, so inserting, so that's great, and that lets us, and then we can forward all the other traffic, and all the TCP connections work, and everything's fine. The next challenge is we want to insert and remove in less than 100 milliseconds. So we don't want people to have a user visible time where things pause, where things get slow, where there's a hiccup. So again, this makes it harder for people to install it. And the problem here is that when we switch this VLAN over, it's actually another VM which does this. And it could be several seconds between when we kind of get the update that it's been switched, and then we can actually go and start doing all this work. So, the other problem is that computers cache these ARPs. So every time you send out a package, you don't send out a separate ARP saying, where do I send this? Send it here. Where do I send this? Send it here. Where do I send this? Send it here. Instead, you cache this value. And usually when a TCP packet goes unacked, which only takes a few hundred milliseconds, you will get a reply. It will send out a new ARP saying, oh, maybe the reason that the packet got dropped is because I got the ARP thing wrong. But not older versions of VMware. Older versions of VMware hold on to it for 20 minutes. So in the worst case, if you did it just after an ARP, if you made the switch just after an ARP, your NFS mounts would be offline for 20 minutes. That obviously is not going to make anybody very happy. So the answer is something called gratuitous ARP. So you can send out, our cache VM sends out an ARP reply basically without a question that came in, right? Without a request that came in. We just send out saying, hey, here's my MAC address. If you want to talk to this storage guy, this 18.10 IP address, use my MAC address. And it's broadcast. It's not sent to any particular thing. Right. So then the question is, when do we send this? So there's this problem that when the VLAN changes, we don't know right away. It's a separate VM that's making this change, and so we have to listen for traffic. So what we do there is we go into what's called promiscuous mode. So one of the changes that happened one of the downsides of back when it was all a coax cable, is of course that your bandwidth, only one side can be using the bandwidth at the same time. So if the first one wants to talk to the second one at, in this case, probably 10 megabits per second, which is the capacity there, and the second one wants to talk to the third one at the same data rate, well, sorry, you can't, because only one person can be talking at a time. With the change to switches, the switch is actually smart enough where it listens to the ARP traffic and says, hey, I've seen packets come in. They say the source MAC address is such, and they come in on port 17. When I see a packet that has to go to that MAC address, I'm only going to send it over port 17. I'm not going to send it to the others. So there's this concept of a forwarding table where the switch learns, just from observing the traffic, no configuration needed, that where to send things. And so most of the time, something that comes in one wire goes out only one other wire. So that's a problem for us. The virtual switch does this as well, and it's not going to send us the packets. We're not going to be able to tell when the VLAN is switched because it's not going to send us that packet by default. So what we do is we put a port into promiscuous mode. Promiscuous mode says, hey, send me all this stuff, even though it's not addressed to me. That's OK. I want to hear about everybody else's traffic too, not just my own traffic. So that lets us tell right away. So now we can see when the host NIC tries to talk to the storage. What's it trying to? We can see when it tries to do that, and when it fails, then we can send out our ARP, our gratuitous ARP. However, we can't do this on the storage side. So remember, the green on the left is something we created, has just us, and the host NIC, it's a very controlled thing because we put only 2 things on it. On the other side, there is the other side is something that was pre-existing, configured, and lots of different configuration options we don't want to mess with. Could be lots of different machines on there. The virtual switches are typically not put into promiscuous mode. Can anybody guess why you would typically not allow? You would just completely deny people putting things into promiscuous mode on a switch? What was that? Yes, security. If you want to snoop on someone's traffic, one of the best ways to do it is to start saying, hey, send me traffic that's not even mine. It's not even meant for me. Trust me, I'll be fine with that. So a lot of switches are set to not even do that. Security software is set to look for this sort of thing and raise flags about that. So we can't do it on that side. So what we do is we send something called an ARP probe. Let's see if I have a picture of that. Yes. So an ARP probe is where you send who has this IP address, but then you don't say who the destination is. Basically, tell 0.0.0.0. So this, for example, is used before you have an IP address. If you're just booting up and you haven't done DHCP yet, so you don't know your IP address, but you're kind of guessing. So this can be used to guess an IP address and find out if somebody has this, or if you know the name of the DNS. If you know the IP address of the DNS server, you can say, OK, who do I send things in order to do a DNS request? But I don't have an IP address for you to send it to. So we send these, and we send these fairly aggressively every 50 milliseconds. I think the spec says we're not supposed to send them that often, but shh, don't tell anyone. So we send them fairly quickly until, and at some point this host switch, which is originally on the right, originally connected to the right to the blue, so this is actually during uninstall. So when the green, when it's unplugged from the green and reconnected to the right to the blue, all of a sudden it will start answering saying, oh, I have this IP address, send it to me. And that's when we know it's been connected, and that's when we can send the gratuitous ARP telling everybody to talk to the old MAC addresses that they used to talk to. So one last piece of information. So this is a distributed cache, right? So if there's information on one host and the same information is on the other host, we can share that, only store one copy of it. So we have a bigger effective size of our cache. In order to do that, they need to talk to each other, right? In order to do this, they need IP addresses. Well, there's a problem getting IP addresses. I thought that just make a DHCP request, get an IP address, and you're good to go. It turns out in a lot of these networks, people don't use DHCP. On your storage network, people, IT administrators assign them by hand. And what's more, the way they tell what IP addresses are in use is by having an Excel spreadsheet. And so we see this because we need one IP address because we have this management server, a web page people go to manage our software. We have to get an IP address for that. And so we'll see on phone calls, they'll pull up a spreadsheet and they'll look for one that's unused, but then they're not sure if the IP address is actually is really unused, if the spreadsheet's up to date or not. So they go into a host and start trying to ping this IP address. But then they think, oh, wait, maybe the firewall is set to block pings, even though it's set to block regular traffic. So then they go look up the firewall configuration or try some other way. So getting IP addresses in these environments is a nightmare. It's very hard for us to get one. We could not get one for each host. If they have a dozen hosts, there's no way we could get a dozen of these. So we have to have them be able to talk to each other without anybody being able to assign us an IP address. So the answer here is something called LinkLocal Addressing. So the spec for IPv4 says that the IP addresses of the form 169.254 should never be routed from one LAN to another. They're local to the link. A link is another word for LAN, essentially. So we generate a random one for each of our caches. So this is great, but there's this problem of you've done this, but then what if somebody else does the same thing, right? So what if there's some other software that has done the same thing, got a link local address, and it's already in use? Well, the answer is you can send an ARP probe. So more ARP magic. This means all of our cache VMs need to be on the same LAN. If there's a router in between, if you have two separate LANs and with a router in between them, and we're trying to talk, then we won't be able to do the deduping. We'll still be able to cache fine and cache within each LAN, but we just won't be able to do a deduping across LANs in that case. But that's not a big deal. Okay, so that's basically the talk. There's a bunch of cool, networking tricks. So the high-level thing is that intercepting IPs without changing IPs, or intercepting I/O without changing IPs is hard. We use a whole bunch of fun things which you may have heard of. So some cool tricks for your toolbox. I won't go and list all of those. You can read those if you're curious. And the moral is that you can put the complexity either on the user or in the software. We can either have users go and get us 12 IP addresses, so we can give valid IP addresses to each of our cache VMs and have them talk to each other, or we can use LinkLocal addresses. And we can do all this magic with ARPs and proxy ARPs and gratuitous ARPs, or we can just tell them, hey, you're going to have to take your VMs down and put it on us. And so it's just an interesting note that the complexity has to be one place or the other. A lot of times people focus on the technology and leave the complexity to the user, but we took the approach of putting the complexity in the software to make things easier for the user. So questions? Right, yeah, got 1 minute and 20 seconds left for questions. with effort. So the question was, how do we debug our stuff? Use TCP dump to observe things going on. You read the spec. In-house, we can control all the hosts that are used. VMware has some decent utilities. We can run something like TCP dump. So TCP dump lets you look at each packet as it goes across. Right? We use Linux for our cache VM, so we can do it there. We can do something like that on the host. We can plug in another physical, we can put a physical switch in promiscuous mode and look at things going on the physical wire. So it takes some effort and it takes a while, but that's the basic technique. Uh-huh. Yep. So for those who don't know, vMotion is you can move a VM, one of your guest VMs, not our cache VM, from one host to another host. So this is a computer, and while it's running, you can move it from one place to another. It basically sends the RAM contents across the wire, kind of stops running it on one place and starts running it in another, and it's all seamless. So for regular vMotion, it doesn't really affect us because that's a RAM transfer. We do have to notice that it was caching here and now it's caching there. For storage vMotion is basically copying things from one NFS mount to another, and that looks like a read followed by a write to us. So that all kind of magically falls out. There's some optimizations we do to have a warm cache on the destination. But other than that, it falls out. All right, and my time is up. So thank you.
Nice. Did not seem as simple.